Hi, my name is Griffin Price, and this is Lab 5 Falling Slinky. To introduce this lab, the purpose of it is to predict the motion of the bottom of a slinky as the slinky is dropped from rest. And as you can see here, I have some results that are mostly similar and I believe are somewhat accurate, my observed and computational. So to get into some fundamental principles, a big one in this lab is going to be Newton's second law, which is F equals ma, and can be rewritten as the velocity update and the position update formulas, which are listed there. Another big component of this lab would be gravity, which all in all is just your mass times the gravitational constant, and then obviously in the negative j hat. So it would always be in this situation it would be in the negative y direction. And another topic or another force I would like to explain for this lab is the drag force, which can be defined by that equation there. And there's a good little image to show you kind of what drag force is. But I also want to talk about another force that I'll call F Slinky, because in this model, you'll see that when the slinky is first dropped, it's extended. And since in this lab we're only focusing on the bottom of the slinky, as the slinky is dropped, the bottom of the slinky stays kind of suspended in air as the top falls, and that force. And you would think that, oh, the bottom should fall too because gravity would pull it down. Well, yes, gravity is acting on the bottom of the slinky, but as you can see, there's a force that's pulling up with the same magnitude of gravity that I call F Slinky in this lab. To explain this further, there's a little graphic of the slinky. So as you can see, the slinky is extended in that image to the left, and the bottom of the slinky is being pulled down by Fg, but it's also being pulled up by F Slinky. So the system is obviously the slinky, specifically the bottom, and the surroundings being the earth, the air, pretty much everything else. And you can see I use tracker to mark the position of the bottom of the slinky throughout every frame of the video. And it's kind of funny. I had to look up the guy on the left, his height, to get a nice reference for the video. So I'm glad the guy on the left was kind of famous so I could look up his height. But nonetheless, the coding I feel like is a lot better representation because as you can see, the first image on the top left there is just explaining the initial position on which I got from tracker, delta t I got from tracker, and b the drag force proportionality constant. I actually had to trial and error with it, so that was a little bit confusing, but I got it to work. And for the mass of the slinky, I just looked up the average mass of an average slinky, and that's what I got. And as you can see on the left, the leftmost image, from time when it's lower than 4.458, I found that from the tracker data to be when it's suspended in air and not moving at all. So I have my weight, which is basically my gravity, acting on it. But I also have Ft, which is kind of like the tension force, which is the slinky force I was talking about earlier, which is exactly the same magnitude as gravity, but just in the opposite direction, which keeps it suspended. And on the right, the image to the right of the code, you can see that now T is greater than 4.458, but less than 8.258, which is the end of the video. You can see that now weight is the same, the gravity is still the same, but there's not really a tension force. What there is a drag force. The drag force is still pointing upwards, but it's not as strong as the gravity pulling downwards. So you'll actually see the force, the net force, is going to be, instead of 0 like how it was before, it is now actually going down, which you can see in the graph in the upper right there. So here's the final results, which the blue is what I graphed, from tracker, and the orange is what I got from the code. Not too bad, I don't think. Pretty good, pretty similar. Yeah, and I think that's good. I think some errors. Obviously, tracker, I have shaky hands, so you can see there's kind of like little the slope kind of increases and decreases and increases and decreases. So might be my sleight of hand, and the computational is more linear. But and the video on tracker was kind of at an angle, so it might have not the just by the angle of the camera in the video might have led me to get some skewed data. But I think all in all, it was a pretty good lab, and I'm so thankful for you watching and listening to my video, and I hope you understand the physics. Um, and just thank you.